Hello everyone, and thank you to the organisers for inviting me to the meeting and giving me this opportunity to speak. And there's going to be considerable overlap between my talk and Raphael's talk, so hopefully it will give you a chance to become more familiar with the concepts and for them to bed down a little bit in your understanding. So I've changed my title slightly to Path Integral Quantum Theory rather than Quantum Measure Theory. That's just marketing, because to me they're sort of synonymous, but I want to use the high regard that the path integral has amongst physicists to reinforce this as an approach to quantum foundations that deserves attention and interest. So I'm going to give just a slightly different motivation for thinking about the path integral, starting with the path integral as a basis for quantum foundations, than the one that the things that Raphael focused on. And that's sort of a historical one. So Dirac is closely associated with the canonical approach to quantum mechanics, but it's not widely known that he's also should be closely associated with what I would consider the alternative, which is the path integral framework. And this is he discovered the path integral very early on in the history of quantum theory. So already in 1932, I think this paper, the Lagrangian in quantum mechanics, was published in 1933, but he submitted it in 1932. So these are all quotations, so the words of Dirac, in this paper. And he writes, quantum mechanics was built upon a foundation of analogy with the Hamiltonian theory of classical mechanics, and no one should know that better than him. There is he says, however, there's an alternative provided by the Lagrangian, an alternative to Hamiltonian theory. And that's provided by the Lagrangian. There are reasons for believing that the Lagrangian one is the more fundamental. Then he gives a couple of reasons. One is that there's no action principle of the Hamiltonian theory. And the second reason is that the Lagrangian method can easily be expressed relativistically, while the Hamiltonian method is essentially non-relativistic in form, since it marks out a particular time variable, this has been cut off here, as the canonical conjugate of the energy of the Hamiltonian. Then in the paper, Dirac shows that if you start with the classical, for the Lagrangian method for classical mechanics, it leads to the path integral. And he showed it comes with its own quick and dirty interpretation, that classical behavior results in a quantum theory as h bar goes to zero from the destructive interference of the amplitudes for the non-classical trajectories. So I think that this sets up already at that point, very early on in the history of science, a choice to be made. I called it Dirac's fork. And you can take two paths. You can choose the Hamiltonian framework for classical mechanics, which Dirac calls essentially non-relativistic. And I sort of feel that part of the reason that it's clear that the majority of physicists have taken this path to quantum theory. And part of the reason, I think, is that when you learn Hamiltonian mechanics, when you really learn it sort of properly for the first time, one can be blown away by its sort of formal beauty. It's rather a lovely, and you can feel that you've finally grown up, as a mathematical physicist. It's really very lovely. And then when you see that there's this analogy between the structures in that classical Hamiltonian theory and the structures that exist in a canonical quantum theory, you think, well, goodness me, this really has to have something to do with the truth. I mean, so taking the Hamiltonian approach and the canonical quantization approach leads you to state vector Hilbert space, and I claim it necessarily means that you have to split in order to make contact with the world of actual measurement results and labs. you have to split the world into a quantum system and a classical exterior in which your labs and measurement devices all live. So you can say, where does Hilbert space come from? Well, you need Hilbert space in order to carry the representation of the canonical commutation relations, which are just the analogous. They're the mirror of the canonical Poisson bracket relations in the mechanical variables in the classical theory. So all of this structure comes essentially from this Hamiltonian framework, and I claim that it necessitates a split of the world into quantum system and classical exterior. However, if you take this route, if you choose a Lagrangian as being the Lagrangian framework as being more fundamental way to think about classical physics, then it leads, as Dirac showed, to the path integral. The arena for what happens is always space-time, and the things that you talk about, the subject of the theory, the thing that the theory is about, are events in space-time. And here I've traced this route. It's not been taken by many, but here are some names of people who are associated with it. Well, Dirac, of course, Feynman in particular, Jim Hartle and Raphael Sorkin, and it's kind of notable that Hartle and Sorkin are both workers on quantum gravity, and as Raphael was pointing out, that this route seems to be a particularly fruitful one for quantum gravity. And I just want to mention that the influence that Feynman Lev said that Feynman didn't think of the path integral as something fundamental and didn't think in space-time terms. I think that's not true. I mean, he may not have said it explicitly, but his lectures on physics, they're suffused with space-time thinking. He's always talking about particles and what they're doing in space-time. And it's notable that...
One brief comment.
Yes.
There is a beautiful paper by Schweber, a review of Feynman's kind of pictorial approach, in which he says what you just said.
Well, I'd be interested to look at that. And one just historical note that Jim Hartle, he was actually at Caltech during the time when the Feynman lectures were being turned into the books that we have. And Jim Hartle told me that he drew all the pictures. I mean, I don't think he's actually responsible for all the pictures that are in the volumes, but he sketched them. I mean, he decided which pictures were needed, and he sketched them, and then they were sent out to someone, a professional artist to actually produce the pictures that go into the volumes. But Jim was, was instrumental in producing those volumes of the Feynman lectures. So I think we can trace a direct influence from Feynman to Jim Hartle. And Raphael was also at Caltech. I kind of probed him a little bit as to whether he can really say anything about whether he was directly influenced by Feynman or not. I think, anyway, we can ask him later about that. So I think that this route is more, I mean, you can trace the history of this path integral space-time thinking rather directly. As I said, it's if you were to make the thickness of these arrows, proportional to the numbers of people who think about foundations in these ways, then this would be really fat and this would be really thin. But I think that's not fair in terms of the intellectual interest and power of space-time and path integral thinking. So I'd like to claim that for unity's sake we should choose the path integral, and by unity I mean at least two things here. So I mean the unity of quantum physics with relativity. Dirac himself claims that the Lagrangian approach in the path integral is more relativistic, and that the Hamiltonian and canonical approach is essentially non-relativistic. So for the sake of unity between, or potential unity between relativity and quantum theory, we should choose a path integral. But also in terms of unity between observer and observed. If you take the canonical approach, you have to make a split in order to get operational meaning from a canonical quantum theory. You have to make a split. You have to appeal to classical measuring devices. Whereas if you take a path integral approach, you never need to make a split. That you can treat everything, observer, apparatus, and quantum system, always together, always within the quantum system. Now so here's a question. What's the nature then of the physical world in a sum over histories quantum theory? But Raphael's already raised and addressed this question in his talk, so I'm going to run through the same sorts of thoughts here. And just mention that there are two main path integral based interpretational frameworks. So one is something called and they're very closely related. So one is Jim Hartle's generalized quantum mechanics, and you can think of this. Jim Hartle's approach to quantum foundations is generally more widely known as decoherent histories. And there's a special version, a special variant of decoherent histories, which is the path integral version, and that is particularly associated with Jim. There are other people who work on decoherent histories, but not from the path integral point of view. It's Jim Hartle who is associated with the path integral form of decoherent histories. And Raphael Sorkin's quantum measure theory, which you've already heard about from Raphael. Both of these approaches deal directly with space-time events. That's what they're about. And particularly from in Raphael Sorkin's viewpoint, path integral quantum mechanics is seen as a generalized stochastic process. It's more like Brownian motion than it is like classical Hamiltonian mechanics. So it's a generalized stochastic process, but with a generalized measure, generalized probability measure, or in other words, a quantum measure, which is given by the path integral. So the path integral provides you with this generalized probability measure. Okay, so in this view, in a space-time path integral view, a quantum theory, in fact any theory, but quantum theory, just for definiteness, has several ingredients. The first thing that you have to decide upon, and this is part of physics, not just decide upon, but discover, is a set of space-time histories. I'll give it this name, omega. So in other words, we have to decide on the kinematics of the theory. And this is hard. This is part of physics. It's not immediately obvious what this set of histories, space-time histories, should be. For some systems, it is kind of obvious what you should choose. So in particular for some n-particle system, say if we wanted to describe the physics in this room just very simply in terms of a large number of particles, then one history would be a trajectory for every one of the particles. So it would be n particle trajectories. That would be a single history for the physics in this room described as an n particle system would be n particle trajectories. Let's say, just for definiteness, between some initial time t0 and some final time capital T. And these histories are what, as Raphael said, are what are summed over in the path integral. Then, secondly, there is this Boolean algebra, as James pointed out. There's a Boolean algebra of events, where an event, again as Raphael mentioned it, is a subset of the set of histories. So, for example, if the system under consideration were the labs of Alia and Bai, and they had experimental apparatus in them, then an event could, let's say A, could be Alia gets the outcome plus for a spin measurement of her spin half particle in the x direction. And another event could be Bai gets outcome minus for a spin measurement of a spin half particle in his lab in the y direction. And each of those events is a subset of the set of history. So there's lots of microscopically distinct histories, n-particle trajectories, which would which are consistent with those two macroscopic events. And this event A consists of all of those histories that are consistent with Alia getting her result. And the event B is the set of all histories which are consistent with Bai getting his result. And the structure of this set of events is Boolean just because they're subsets of some universal set of histories, omega. And an event, it's just at this level an unasserted proposition of the world. It may or may not happen in the real world that Alia gets that outcome. So it's just, and Raphael mentioned, a nice way to think about this is that you can think of an event as a question about the world. Will Alia get this outcome? Well, it depends. Sometimes she might not. So it's at the level of this event algebra, these events are just, they're unasserted. We're not saying whether or not they actually happen. They're just potential. They have a potential for happening, and they correspond to questions about the world. Okay, so the theory has this set of histories. There are events, in other words, a set of questions that you can ask, and those questions have this Boolean structure. And then they have a dynamics. A theory has a dynamics. And in a quantum theory, that dynamics is given by the path integral. And the path integral provides for you a measure. That is a number, mu of A, positive number. For any event, any possible question, there's a number, mu of A. Non-negative number. In a classical theory, this measure is a probability measure. So for Brownian motion, for any event, any measurable subset, there will be a number for that associated to that subset. That would correspond to the probability that event happens. And in a classical theory, the possible physical worlds are just single histories in this set of histories. And so another way to interpret this measure mu of A is as the probability that the realized history, that single history which is realized in the actual run of the dynamics, the actual Brownian trajectory, is in the event A. So you can say, these are just the same way of saying the same thing. Two different ways of saying the same thing. Mu of A is the probability that event A happens, or mu of A is the probability that the realized history is in A. And in classical theory, those are the same concepts. In a quantum theory, the measure of an event A is given by the path integral, and I have actually written it in a little more detail here. It may look a little unfamiliar, but it's the familiar square of the sum of the amplitudes for all the possible ways that a particular event can happen. So the slightly unfamiliar thing here is that the two histories, gamma and gamma primed, have to be tied together at the end. They have to, their final positions, gamma and gamma primed, at the final time that you're considering, have to be equal. That looks a little strange when you first see it, but it's really just, it's because of the fact that when you calculate the probability measure, the probability density for, say, the position of a particle, it's psi star of x, psi of x integrated over x. So psi star and psi have the same argument. You don't integrate psi star of x1, psi of x2 over x1 and x2. So this delta function, it looks weird, but it's really just the fact that the probability distribution is psi squared. And the amplitude in quantum mechanics is just the usual one. It's the e to the is, where s is the classical action of the trajectory, and weighted by some initial amplitude. Okay. So in quantum mechanics, mu of A is sometimes equal to the probability that A happens. And that is true whenever A is an instrument event. So some macroscopic event like Alia getting a particular outcome when she does a spin measurement. And it is the Born rule probability. So the path integral contains within itself the operational Born rule probabilities. And it does so without having to make a split. You don't have to put the instrument outside the system. You can maintain it within the system, and the path integral gives you the probability. And also, moreover, if an event could be measured by a hypothetical ideal measurement of some, or a sequence of ideal measurements, then mu of A is equal to the probability it would be measured to happen, were it to be measured. So these seem like the same thing, but I'm saying something slightly different. Here, I think in the system there is a measurement device, and the measurement device showing one particular outcome is an event that is in the event algebra, and you can calculate its measure, and you will get the Born rule probability for that outcome. This is something slightly different. There is no measurement device here inside the system, but if you can conceive of there being a measurement device, even though there isn't one in your system, there is no measurement device. You're not describing the measurement device in the system. But if you can conceive of one, and you can see how it would be possible that you could make an ideal measurement of an event, then this quantum measure, mu of A, this given by the path integral, is the Born probability that it would be measured to happen if you did measure it, but you're not measuring it, and there's no measurement device inside the system. So it has a very close connection to probabilities as we know them and understand them and use them, but it's not a probability measure. And it's not a probability measure because it doesn't satisfy the rule, the Kolmogorov-Sun rule for being a probability, exactly because of interference. So here A and B are mutually disjoint events. A union B, that's A or B, and the quantum measure of A or B is not the sum of the measures of the individual events A and B, because there's interference between A and B. There are cross terms when you calculate the path integral. You calculate the path, it's a double sum, it's a sum over the histories in A and B twice. So you get cross terms between the interference terms between the histories in A and the histories in B. So what to do in this case? How are we going to, if we want to go beyond the operational use of this quantum measure to just referring to instrument events, if we want to go further, do more, how do we use this mu to do physics? And Raphael's already mentioned that what we're in the first instance pinning our hopes on is what he called the preclusion principle. I just called it a rule here, which is that if the measure of an event is zero, if it has zero measure, then it doesn't happen. So if mu of A is zero, then A does not happen, or almost surely does not happen. And that seems pretty minimal. I mean, one might not think you could get a lot from that, but we can already draw a powerful conclusion, which Raphael has told you, but I'm going to give you a specific example, which is a lovely example that may be familiar to some of you. It's a Koch and Specker contextuality and non-locality example all rolled into one, and I'm going to turn it into a sort of retro-causality example as well. So this example is just the example of the GHZ state, which is really pretty symmetrical and lovely in all sorts of ways. So I'm going to run through the standard way of thinking about the GHZ case, GHZ state in ordinary, in the way people normally think about it, and then I'm going to turn it into an example that we can think about in quantum measure theory in terms of histories. Okay, so what's the GHZ example? Well, it's a Koch and Specker like example, but it's state dependent, whereas the original Koch and Specker theorem is independent of the state. So there's a special state, the GHZ state, and it's a state of 3 spin half particles. And here I'm ignoring all normalization. Everything that I'm going to say is in terms of, is sort of in logical terms and not in terms of anything, any actual values or normalizations or anything. So I'm just missing out all normalizations and all factors of h bar and 2, right? So yeah, h bar equals 2 equals 1. So this is the GHZ state. It's the superposition of all the 3 particles being spin up in the z direction and all of them being down in the z direction. So that's the GHZ state. And this state is an eigenstate of 4 operators. I call them P, Q, R, and X. And in everything that I'm going to do, I'm not putting 1, 2, 3 labels on the particles 1, 2, and 3. That's implied by the order in which I write things. So I'm always referring to particle 1 first, then particle 2, then particle 3. So P is the product of the spin of particle 1 in the x direction, the spin of particle 2 in the y direction, and the spin of particle 3 in the y direction. Q is the product of spins of particle 1, 2, and 3 again, but this time particles 1 and 3 are in the y direction and particle 1 is in the x direction. R is again the product of 2 spin y's and 1 spin x. This time the spin x is for particle 3 and the spin y's are for particles 1 and 2. And then x is the product of the spins of the 3 particles all in the x direction. So those are 4 operators. And it's very simple to show that the GHZ state is an eigenstate of all these operators up to factors of h bar and 2. This is what you have. Sigma x just flips spins, so it turns all of the so sigma x of particle 1 here flips this up spin to a down spin, up z spin to down spin z spin, and vice versa. It flips this down spin to up spin, and y flips spins but with a factor of either I or minus I. And because you do 2 y flips, you either get I squared or minus I squared. So you get this term turns into this term, and this term turns into this term, but with an overall minus sign. So P acting on psi is minus psi. Similarly for Q and R, so psi is an eigenstate of P, Q, and R with eigenvalue, with a negative eigenvalue. Whereas X just flips all the spins, so it obviously leaves psi invariant. So psi is an eigenstate of X with eigenvalue plus 1, or positive. Oh, forget the h bars and 2's and everything. And famously, there is the thing about this system is that there's no non-contextual assignment of values to the 6 spin variables. In other words, x and y spins for particles 1, 2, and 3. That's six spin variables. You can't assign values to those spin variables anyway. There is just no assignment which is consistent with these predictions, with these quantum predictions. So you can see that because if you were to assign spin values, each of these spins would have a value, let's say plus or minus 1. If you multiply them all together, so multiply P by Q by R by X, then each spin occurs twice. So you get sigma x squared, because sigma x is here and it's here, so you get sigma x squared. So everything is squared. And so that number is positive. However, if you multiply this by this by this by this, it's negative. So there's no assignment, non-contextual assignment of values to the 6 spin variables, which is consistent with the quantum prediction. Here's another way to describe that, say that same thing. So if I consider the set omega, and that's suggestive, I've used that letter suggestively. So omega is the set of all the possible assignments of values to these spin variables. So it's a 6-bit string. So there are 6 bits, sy for particle 1, sx for particle 1, sy for particle 2, sx for particle 2, sy for particle 3, sx for particle 3. Each spin takes values plus or minus 1. So that omega has 64 elements in it. So it's 64 6-bit strings. Here it is. And there are certain subsets of that set of 6-bit strings, which are the disallowed subsets. So let P correspond to the operator P, be the set of strings such that the product of the x spin of particle 1 times the y spin of particle 2 times the, I think that should be y, sorry, that's the typo, that's y. The y spin of particle 3 is equal to minus 1. Remember, the quantum prediction is that it's negative. Right? So here, this is the set of strings which violates the quantum prediction. Right? It's the wrong sign. So it should be minus 1. So P is a precluded set of values. It's all the sets of strings such that Sx times S of 1 times Sy of 2 times Sy of 3 is equal to plus 1. That's precluded by the quantum prediction. It's not consistent with the quantum prediction. So you can't be in set P. So none of the strings in set P agree with the quantum prediction. So you can't have that. Q, similarly for Q, that's precluded because, again, Q is the set of strings which violates the prediction that you get by looking at the operator Q. R is the set of spin value assignments, which is precluded, which is ruled out by looking at the R operator. X is the set which is ruled out by looking at the X operator, and X is the union of the complement of P, Q, and R, together with these regions here. My drawing skills let me down here. I could have shaded it in a lovely way. I just didn't know how to do that. So X is the complement, everything out here, and these regions here which intersect with P, Q, and R there, but not the region in the middle. Okay, so it has a lovely symmetrical character. In fact, in every one of these sets, P, Q, R, and X, there are exactly 32 histories. In each of the individual regions, there are actually 8 histories. So there are actually 8 regions here, 8 little regions, and they each have 8 histories in them. Okay, so you can't be in P, you can't be in Q, you can't be in R, and you can't be in X. So there's nowhere to be. So there's no spin assignment that is consistent with the quantum prediction. Okay. Now, that's the argument for contextuality in the GHZ for the GHZ state. I'm going to turn that into a histories, into a system in which we can talk about histories, space-time histories. So we have 3 particles in a GHZ state, and we send them along to 3 different directions, and we do the same thing to each of them. So particle 1, for example, goes along, and here it's split into 2 beams via some Stern-Gerlach apparatus. So it either goes in the upper beam or the lower beam, which I've denoted by plus or minus. And the Stern-Gerlach is aligned so that it corresponds to spin in the x direction. And then there is what Raphael described as a recombiner. So it's just a Stern-Gerlach apparatus in which you reverse the direction of the magnetic field. So whatever this beam splitter did, this recombiner reverses, and this state here is just is exactly the same state as what went in here. The coherence is regained here. So no measurement in terms of destruction of interference, destruction of coherence occurs here. So the particle splits into two beams, but then it's coherently recombined afterwards. Then you do the same thing to the particle, but instead the apparatus is aligned in the y direction. You split it into two beams, and this time we could imagine detecting it at the end, but we don't have to. It's just going in the upper beam or in the lower beam, and then we stop it there. That's the final time. Okay, so it actually doesn't matter to the analysis whether you actually have a detector here or not. And then you do the same thing to all of the other two particles. So particle 2 gets sent through an X direction beam splitter and recombiner, and then a Y one. And then particle 3 gets sent through an X spin beam splitter and recombiner, and then through a Y one. Okay, and just for future use, notice that I've drawn this in this way to say that we're sending them in different directions, but I'm later on going to think about particles 1 and 2 as being in the same lab and particle 3 as being somewhere else, and we can choose this lab here to be space-like, and everything that happens, the timings of the particle passing through these beam splitters and recombiners, to be such that it's space-like to the particles passing through here, or we can delay it so that this happens later than these two. So we can just make it hang around for a while and then send it through X and Y later than 1 and 2 pass through their beam splitters and recombiners. So what happens in lab 3 happens either space-like to 1 and 2, or it happens later. That won't actually matter to the analysis I'm going to show you, but it will matter to the interpretation of the result. Okay. Are there any questions about this setup?
One technical comment, that it would be nice to amend to it a Minkowski diagram of the same things that you can see what is space like for
Sure.
future use.
Yes, sure. Yeah, this is just space here. Yeah, it's just space. Good. So, this is exactly the same slide as I had before, but now this omega has a different meaning. The elements of omega are histories for this system. They're space-time histories for what the three particles are actually doing. So one history, for example, would be, one history corresponds to 3 trajectories, one for each of the particles. So one history could be, for example, particle 1 goes through plus beam and then minus beam. Particle 2 goes through plus beam and plus beam. Particle 3 goes through minus beam and minus beam. Okay. There are 6 beam splitters, so that's 2 to the 6. There are 64 possible histories, and we can label them with exactly the same variables that we had before. In other words, the spin values. So Sy is just +1 if particle 1. So again, this is all in order. So particle 1 is these two variables. Particle 2 are those two. Particle 3 is those two. Particle 1 going through the plus beam, the Y plus beam, that would correspond to Sy being +1. Particle 1 going through the X minus beam, that would correspond to X being -1. So there are 64 possible histories. Each history, remember, is 3 trajectories, 1 trajectory for each of the particles. Okay. So this is now the set of space-time histories in the path integral. And we can again consider these sets P, Q, R, and X. So P is defined exactly as it was before. P is the set of all histories such that Sx1 times Sy2 times Sy3 is equal to +1, which remember is the wrong sign, right? That's the thing you don't get. Because it's the wrong sign, that means that when you calculate, which I'm not showing you how to do it, but when you do calculate the quantum measure for the event P, remember it's a set of histories, it's an event, we can calculate the path integral for it, the quantum measure for it, you get 0. And you get 0 for exactly the same reason because the GHZ state is an eigenstate of the operator P with the eigenvalue -1. So that the quantum measure of P is 0, so P doesn't happen by the preclusion rule. Quantum measure of Q is 0, that doesn't happen. Quantum measure of R is 0, quantum measure of X similarly 0. They're all 0, they're all precluded events. And that means this is another example of, to put in Raphael's list of examples that shows you that in quantum measure theory in general, in path integral quantum theory in general, if you adopt the preclusion rule that null events, in other words events with measure 0, do not happen, the physical world can't be a single history. Because if the single history, so choose a single history, any single history at all, is going to be in a precluded event. And that would mean that event happens, but it doesn't happen. So the physical world can't be a single history in this system. And if it's not a single history, then what can it be? And this is work in progress, so that we don't know the answer to this question. But a currently favoured proposal, a particular interpretational scheme for path integral quantum theory, is that the physical world is just a set of histories. A set of histories which is as small as it can be whilst remaining consistent with the preclusion rule, preclusion principle. So this is just a restatement of Raphael's, what he called the multiplicative scheme. It's, in some sense, the simplest possible generalization of the classical view of reality being a single history. It's just a coarse-grained history, something which is a little fatter than a single fine-grained history. It's a set of histories. So, and now we see a way out of our impasse here. If reality can be a set of histories, then we can evade the no-go theorem that we had before. And in particular, let's just assume for a moment that the only sets of measure 0 in our system are P, Q, R, and X. Those are the only sets of measure 0. There are no other sets of measure 0 that no other preclusions that we have to worry about. Then, if you take any two histories, I've drawn an example here, gamma and gamma primed, which don't lie in a single one of the null events. So the gamma and gamma primed here are not both in P, Q, R, and X. Then that is a viable or possible physical world, because it doesn't. If the physical world were gamma and gamma primed, then it doesn't imply that any of the precluded events happen. So that's a possible world now. And if P, Q, and R and X were the only null events, then there are obviously many possible worlds that you can have. Any two histories like gamma and gamma primed, which don't lie both in any of the null events, is a potential world. There are other null events, however. It's more complicated than just this. There are other events of measure 0, other preclusions that you have to take account of. But it's not fantastically difficult. You can identify all these other null events. You can work out what they are. And they were worked out by Dionigi Benincasa and Michael Buck, who are here. So this is a complete solution of this GHZ system. These are all the possible worlds. Raphael called them co-events. And I'm using possible world to be synonymous with co-event. And what I'm showing here are what Raphael called the supports of the possible worlds. So they're sets of histories. And let me just explain this notation here. So this notation of 6 symbols, 3 on top and 3 below, those are, each one of those is a history, and it's just these, it's the spin values. The top row are the Y spin values, and the bottom row are the X spin values for particles, and then, again, it's ordered 1, 2, 3. So this, for example, that's the Y spin value of particle 1. And here, for this history, this one down here, that's the X spin value for particle 3, for example. So this is a possible world. It consists of 2 histories, this one and that one. And the possible worlds break up into 8 collections. And the 8 collections correspond to the final spin values in the X analyzers, the X Stern-Gerlach measurements, because they all decohere with each other. I said it doesn't matter whether you put final detectors at the end. So imagine that you actually detect them at the end. Then those detection events, they're macroscopic, they decohere with each other. So there's no interference between the different final events. And you can think of them, in some sense, as just separate little systems. You're post-selecting on the final outcomes, if you like. So you can think of all these as just being separate. So if the final outcomes are plus 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 for the X spins.
Y, you mean?
Oh, sorry.
Y was done second.
Was it?
In the diagram.
Yes, you're right. I'm sorry. Maybe I've been saying yes. Yes. So Thank you, Jeremy. So these are the Y outcomes. Plus plus plus. You get final outcomes for the Y measurements, Y spin measurements of plus plus plus. Then so you can basically ignore the bottom row here. They're all plus plus plus, all of them. They all agree with plus plus plus, and it's just the X spin values which are non-trivial. So in this possible world, there are 2 histories, and the X spin values are plus, minus, minus, and minus, plus, minus for particles 1, 2, and 3. Okay. So we could stare at this for a while and pick apart a few things. Let me just mention, for example, that if the possible world is this, corresponds to these 2 histories, it's indefinite what the value of the X spin value of particle 1 is, because it's plus in this history and minus in that history. But it's definitely minus for the Y spin value of particle 3, because it's minus in both. Okay, so okay. However, you may have already noticed or been thinking ahead to the possibility that there's lots of choice here. In particular, there's a choice of which order you send the particle through the X analyzer and the Y analyzer. So we could reverse the order in any of the labs, but let's just imagine that we reverse it in lab 3. So we do the Y, we send it through the Y beam splitter first, and then the X one, just in particle 3, and we leave labs 2 and 3 alone, 1 and 2 alone. That gives you a different quantum measure, a different set of preclusions. Still P, Q, R, and X, those are precluded sets still, but there are other preclusions which are different from the case where you have this in the reversed order. So you have different sets of preclusions, you work out different possible worlds according to the preclusion rule. And these are the possible worlds in that case. So they just look, you can see they look very different. So in fact, for some of the final outcomes, there are no possible worlds at all. You just never get those final outcomes. So, and then you can see that all the possible worlds actually have 3, correspond to sets of 3 histories rather than 2 in the previous case. So the possible worlds look very different. And, moreover, if you just look at the possible worlds restricted to questions that you can ask about labs 1 and 2, they are different. they depend on whether you choose the order of the analyzers in lab 3 to be X first and then Y, or Y first and then X. So the next, so don't worry about that too much, but the next slide is more, it's still a bit daunting, but it's more relevant. Okay, so what is this? This plus plus implies that you get plus plus for the final spin measurement of particles 1 and 2, right? So forget about all of this down here. Let's just concentrate on this upper first bit of the table. Above the line here, these are all the possible worlds for particles 1 and 2, given that you did the X measurement first and then the Y measurement in lab 3. These are the possible worlds for particles 1 and 2, given that you did the Y measurement first and then the X measurement in lab 3. And you can see that the sets of possible worlds are different. It's slightly peculiar that I haven't understood this exactly completely yet, but the set of possible worlds for in the second case where you do Y first and then X in lab 3 includes the worlds for the possible worlds for the other case, but there are extra ones, and these extra ones all have they all have 3 histories in them rather than 2. Okay, so in particular, this possible world, this is a possible world for particles 1 and 2. That is a possible world only if the Y, if the order in lab 3 is Y and then X. You can't get this. This is not a possible world for for particles 1 and 2 if the order in lab 3 is X, Y. So this world is possible if one order is chosen in lab 3, which remember is we're putting it is not either space-like or to the future of labs 1 and 2. But it's not possible if you choose this order. Yes, thank you. Sorry, I'm done. Okay. So the set of possible worlds for particles 1 and 2 changes depending on the order of analyzers for particle 3. If we put lab 3 space-like to labs 1 and 2, that's non-locality. We've got or if we put it later, then this is a premonition. Particles 1 and 2 have some a lack of free will in the choice of order for in lab 3. Now, I'll just skip over this because if you read it and find that interesting, you can ask me in the question time. Yeah, I'll stop there actually.